parking. Is it true?
Not that I know of. I haven't heard anything.
Well, that's what I saw, that they wanted to return. They wanted to return, so make it hard for us. Well, I'll have 20 students. That's nice. Okay. Today, but I want to have just a few assignments, announcements first. So you have assignment number 3 that I emailed to you. This assignment, okay, Mr. Al-Masri, hello. Hi.
Sir, how you doing?
I'm good. I'm talking now. Yeah, you have to respect that. And by the way, all of you have your mics open, so be careful, guys. Try to not speak if I'm not asking you to, so that we can control it. Otherwise, it becomes unmanageable. Not a good idea. That's why I opened the chat room in case you have a question, and because I'm going to share later on files. It's the PowerPoint, and we'll talk about it. Then I will not be on the page of where I see the chat, so I'll have to unshare and then go back to see if there are questions. But you are more than welcome to ask, and not necessarily I'll be able to answer all of them or right away. But I'll ask you later on to use the mic and try to ask a question, and then I'll try to answer. Okay. So the assignment is about the next 2 inventory models that we are going to discuss today. I sent to you by mistake an Excel file that has 2 spreadsheets. I emailed about it yesterday. The first one, maybe it's called problem 2, I think, problem 1, problem 2. One of them is not needed. You can delete it. I just forgot to delete it before I sent it. And on the other one, I give you a little table in which you have to select your choice from the multiple choice questions that appear on the Word document. In addition, you have 3 computational, very, very short computational problems that you have to type in the solution, your solution on the Excel itself, and then attach it to an email. But I'm asking that the email will be independent of the one I sent to you. Don't reply. What happens with Gmail, when you reply, it will put all your answers under one umbrella or 2 umbrellas, and I have dozens of students under the same. I may miss names. And then I email to you and say, hey, where is your test? And you say, I email it to you. Then I start to look for, and it's hiding inside other 20. That's how Gmail does it. So it's better that you just form your own email and attach it and then send it to me. I have only one name under this email, and this way I can immediately identify it and put it on the right section and look at the file and copy and paste your answers to my spreadsheet, and there will be no mistakes, and it will be very fast. So that's about the assignment. The assignment is covering the quantity discount inventory model and the production lot size. Both will be discussed today. Okay. So, and then, okay, just a reminder, last time I checked, the quiz, the 3rd quiz, is on either the 20th or the 21st of April, depending on which section you belong to, Monday, Wednesday, or Tuesday, Thursday. So on these 2 days, there will be quizzes. It's quiz number 3. It will have the same format like the exam. Of course, it cannot be like quiz 2 that I already graded. And then about what will happen with the upload. I am going to record this meeting. Once I start, I'll start recording, and it will record all the discussion. It will record the PowerPoint that will be on the screen, and it will go up as a video. You know that, you have seen it before. Then I also am going to upload the PowerPoint files that I'm using today. Now, these are very similar to the PowerPoint file that I sent to you, but since then I made some upgrades on that same file, and I separated it in files, one for each model. The one that you have include both models. So once you get the PowerPoint from me today, you can scrap the other one. It's the same, very similar, but I added some explanations for having nothing better to do. Last week, I did that. And so I think it's now better. And I'm using it today. So you will have it both on the video and independently as a PowerPoint file that you can download. And now one word about PowerPoint, you probably have noticed already that I am building the PowerPoint as a step-by-step progress. It's not that you put a slide and you read it from A to Z and then you go to the next slide. This is exactly what, to use the word, I hate. But I try to use it as a learning tool and a teaching tool. So that's why it's broken down into steps. I'm going to use these steps now today, so you will see how. And then when you work on it yourself, you can use the same steps and the second, but in your own pace. There is no recording going though, because you have the recording for the video. So it's even better. So just pay attention and be patient when you go by these steps. Sometimes there is an animation that takes a second or two to finish. Don't stop it, let it go, because many times those animations has a meaning. And you will see as we are talking about it yourself. I will not even have to tell you that. So let it finish, and then you click again. And then at one of these clicks, it will move to the next slide on its own. So that's about the PowerPoint. So any question you want to ask me, anyone, or you have mics and I'll listen and see anything?
Yes.
Yes, please.
So from this point forward.
Mahmoud?
I'm sorry?
Who is
This is Hector. From this point forward, is all the lectures basically going to be the final? Like from this point forward, everything that you teach us will be the last?
For the last exam.
Right.
Yeah, of course.
Okay.
Since I already tested you on the EOQ model, I tend to not repeat it. Although you will see that the models in inventory are all based on EOQ. Heavily. So you will have to know it, but you will practice it, I think, quite a few times. You will remember it. The EOQ per se will not be asked about, but behind the scene it is. So just wait for a minute and you'll see why. But yes, and then after we are done with inventory, on Thursday we'll finish the last inventory model. So we'll have 2 today and 1 on Thursday. Then we'll start a new chapter. It's chapter 12 from the book. Okay, it's about linear programming. It's not computer programming. You are not learning any language there. It's about a mathematical procedure and a very, very strong tool. So I want you to be exposed to that, at least at the introductory level. And that's what we'll do till the end of the semester. And I think the semester is over, what is it, April 30 or May 5th or something like that. And we are returning, I think, for now, at the end of the month, but I don't think they will even open it. I don't know how the school is going to go about finals. They didn't tell me yet, or anyone yet. I can just tell you that there are some discussions among the faculty and the Senate, academic Senate, and the president, actually system-wide. It's not only our to give, instead of grading students, to give it pass-fail grades in the course.
Isn't that our option?
They didn't decide. I don't want to tell you that I know what will happen. Nobody knows. There is going to be a discussion, campus-wide discussion among faculty, but there are quite a strong movement among faculty per request, I don't know by whom, to do it. And so this is one option. Just telling you, don't tell anyone I told you, because it's not a secret. Hey, you are part of it. But there is such a discussion. Maybe, I don't know. I would ask you, if you want a pass or fail, or you want to be graded. I bet the better students will want it graded, and those who are about to fail will want it fail or pass.
Right.
That's what I think will be practical to say. But to tell you that there is a decision about it, no. And there is still time to decide. We have a few weeks before the end of the semester, and I'm sure I'll be notified. Not only me, every student. If the chancellor is the one who is making the decision for the whole system, after consulting with presidents in the campus, then they will let the president know, and the president will send an email to everyone, or the deans will send it to everyone, or the chairman in the department will get announcement and send it to everyone. But we don't know.
Okay, thank you.
Okay, so what I'm about to do after this class, I'm going to upload our discussion recorded with the PowerPoint, plus the 2 PowerPoint files that will replace the one that I sent you earlier. And it will be in one folder, as you saw before. And Zoom is calling this folder by the date and the time. Okay, so you'll see April 7th. So you'll see 04/07/2020. And then the time will be, I guess, 13:00. And this will be the only file of the 4 classes that I had with you yesterday and today. This is the one I'm going to upload. And so everything at the same time. Okay. I'm suggesting also, you will read the text that I tell you, because the examples that you see today, all the presentation is taken from there, and I organize it in a PowerPoint and to talk about it. So if you read, it will look familiar to you. And look at the examples that by definition are more detailed in the book than I can do here. But it's the same set of examples. Cover only 2 models. Is quantity discount, the one that I'm telling you to cover, and one is production lot size. And on Thursday, I'll tell you what is the 3rd model I would like you to cover. Okay, so this is my introduction for now, and I would like to start sharing, but I'll record first. Yeah, you know, when I'm recording, I have to convert it because I recorded on my computer, not on a cloud, on my computer. So the computer needs to convert it into MP4, and it takes time because the file is huge. So it is converting it and then let me know that it's ready. Then I put the PowerPoint file in the same folder and upload. It takes time, so don't expect it in minutes after our presentation. But it will be today afternoon. Okay, I'm going to share. Okay, this is the file. We are in inventory models, and today we are talking about quantity discounts. Discounts is an issue that any retailer is being involved with. Every production system is experiencing. It's something that is offered by sellers to buyers. Sellers are offering to buyers, hoping that the buyer will increase the regular order that he is following. Buyers will accept this offer if they are not getting hurt by doing it, and even more than just getting hurt. A quantity discount schedule is simply the chart where all the discounts appear. So you will see on one column the quantities of the order size, and then you will see another column with the unit cost. And you will see that the unit cost drops as the order quantity is increasing. The order size where the price is changing is called breakpoint. I'm mentioning it to you because in the template at the end of our presentation, that's the name it's used. Today we are talking about one of the next two types of discount plans. The all-unit discount schedule is the one we are going to talk about, and the one we are not, I'm just going to mention to you for you to see what the difference between them is. The all-unit schedule is the one we talk about, is one in which all the order size, once discounted, the whole order has the same unit cost. The incremental schedule is not like this. There may be more than one unit cost in one order. Why is it so? Is here. So here's an example for all unit schedule. Suppose you are required to pay $15 per each unit if the order size is between 1 and 99 units. Okay. And then if you order between 100 to 299, you have to pay only $13 per unit, so $2 discount. If you order 75 units, obviously you will pay $15 times 75 because you are in the first range. But if you order 125 units, now you will order 125, but the unit cost will be $30. All the 125 will be charged $13. That's one type of a discount. Comes the incremental, and the example is a bit different. So for the first 99 units, you pay 15 as before. Here, for the units between 100 and 299, only those from 100 to 299 will get the discount. So if you order 75 units, your cost will be as before, 15 times 75. If you order 125, your order will be 15 times 99, plus 13 times another 25. So only 25 units are now discounted. The first one paid the first price. The difference between them, which leads to completely different optimization mathematical procedures, is that here, for the same order, you have two unit prices. This is much harder to solve. And here, all the order has a single order. Therefore, here we can use EOQ. That is, if the rest of the assumptions of EOQ are met, and they are, the only assumption that is not is that the unit cost depends on the quantity. In EOQ, it's not like that. So we relax this assumption, let the unit cost change based on the quantity, but once it's changed, all the order is the same unit cost. So you can use EOQ model. In here, you cannot. Just to give you an idea, where is the difficulty? If I order 125, how do you calculate holding cost here? If you have 2 unit costs, you have 2 different unit holding costs. Now you have 2 units. Which unit of the 2 costs you sell first? Are you selling first the $15 until you are finishing 99 units? And then you hold the other 25 units in inventory, not touching them, and only then start to sell them. Then the holding cost is for those here for average inventory is 45, 49 and a half. And here you don't sell at all. Or you don't, or you switch it, or you mix it, or you take the average. How do you calculate holding cost? That's an issue. And therefore, this approach is much harder to analyze. And if I wanted to cover it, I would just turn to the template. Will not be able to explain the concept because mathematically it's more involved. And I thought with the conditions that we have here, even in the regular class, I tend to not touch it. Both discounting schedules are popular. This is easier to handle. So to introduce the concept of discounting and how to obtain an optimal policy, I decided to go with the all unit schedule only. Okay. So the all unit discount can be solved by applying the EOQ multiple times for each discount separately. The incremental discount needs another optimal procedure, so that's why we are not dealing it. The EOQ is something we are familiar with, and that's the one we are going to continue with. The cornerstone of the whole method is the calculation of the total cost. Now, it's important to notice, to find the optimal order size, Q star, EOQ, with a square root formula on EOQ model, we don't care about what the purchasing cost is because this is a constant. It's the unit cost times the demand. And it's the same all the time because the unit cost is not changing. As you look at the quantity discount model, the unit cost depends on what discount you received. So for each discount, we have to apply a different purchasing cost. And this must be part of the optimization. So the total variable cost, which is the sum of the first two, is not enough. You have to add to this the total purchasing cost. That's why the cornerstone is the total cost itself. If you look at, you see the average inventory. So we are applying EOQ system here. You have constant demand, you have a unit cost that is not changing over time, you have infinite horizon, you don't allow for shortages. All the EOQ assumptions are there, only that the unit cost depend on the quantity. So total cost for I here represents the discount level. The discount level can be 0 to any number. 0, it's when you have no discount, and then 1 when it's discount level number 1 and 2 and 3, depending on how many discount levels you received from the seller. And so you calculate the holding cost here as the average inventory times the holding cost of level I. Why is it that it's of level I? You'll see in a minute. Then you have the ordering cost. Here, D divided by Q is the number of orders per year. This is the same like in EOQ. And then you multiply it here by CO because the ordering cost per order is not affected by the discounts. The discounts is given to the unit cost, not to the ordering cost. So no I mentioned here. And then you add the purchasing cost of level I, obviously. And just in case there is safety stock, then you have to include it also with the index I. And now let's see why. Why is it that the holding cost per unit per year has the index I? Because look at the bottom here. CH of I is the holding rate times the unit cost. But the unit cost depends on the level of discount. So it's H times C of I. Therefore, CH is depending on the unit cost. Okay, on the level of discount. This is how we will determine later what is the optimal order. In order to demonstrate the idea, I'm looking at an example that you have looked before when we did the EOQ. It appears in the first file that I gave you. It appears in the book, in the text I gave you. So this will be the chart, the schedule of the quantity discounts. The seller is coming to you, you are the buyer, you are playing the buyer now. And he's telling you, if your order size go between $1 and $2.99, you will pay $10 a unit. This is actually the unit cost that you saw in problem AAC when you started it. Then there were no discounts included. Now we include them. Level number 1 now, it's this one. Level number 1 includes 25 cents discount per unit. So the unit cost is $9.75 if your order size goes between 300 and 599. And incidentally, 300 is here the breakpoint. For level number 2, you get 50 cents discount, but you have to order from 600 up to 999. Then you have 60 cents discount, and then you have $1 discount. This is the schedule. This is the chart we are going to build our analysis on. Just one point as a comment, I'm telling you, to give a buyer a good discounting chart by the seller is an art. The seller is trying to change the buyer's behavior. So he has to know how the buyer is making decisions. In this case, economical decisions. So he has to know what is the buyer's holding rate. He has to know the buyer's demand. He has to do the calculations before he is giving the buyer the chart because he wants him to increase his order. So he has to make sure that the buyer will do it, and the buyer will do his own calculation. So a seller needs to know what chart serves him the best because he wants to reduce his own holding costs. A seller gives such a chart to a buyer if he experiences too much inventories of his own. He's trying to reduce his own holding costs, so he's offering this discount. But he wants the buyer to respond to that. So the seller wants to maximize his own profit, while the buyer should not pay more than what he's currently paying. So that's the essence of how to build such a chart. Just to remind you, the problem that you did in the EOQ model had about juicers that are being distributed and sold. And this is the demand per year. And this will be the holding rate, the H, 0.14. And this is the unit cost, as you see, $10, no discount. Here's the ordering cost. And the EOQ came up at 327, a little bit rounded. You have 2 times the demand times the ordering cost, dividing by the holding cost, square root, 327. That's what the buyer is experiencing now, and he has a total cost for that. So now the question for the buyer is, should he stay with this policy or move away and take advantage of the discounts? So there are a few steps that the buyer needs to follow. Again, we are playing here decisions from the buyer's point of view. First, he has to find the Q star, that is the EOQ value for each discount level I. Here are 2 examples. Q0, you already have seen it, is the EOQ for no discount. When it's no discount, you put 10 here. It's H times the unit cost, give you CH. 327 is something we already know. Then here's another example, Q sub 1. This is discount level number 1. Right now, it's $9.75 per unit. Not 10 anymore, $9.75. Because you divide by a smaller denominator than what you divided here, and the numerator is remaining unchanged, this order is now larger than this. But this is exactly the essence of all the discount procedure. The discount convinces the buyer to increase his order. That's exactly what the seller wants to do. So we go now, here is a summary of all the discount levels. Discount 0 gave you for $10 per unit 327. Number 1 for $9.75 gave you 331, and so on. You see, look how the order size is getting larger as the unit cost gets smaller. Now, what's the issue here? The seller is hoping that the buyer will go for the larger orders. The buyer will agree to do that based on total cost comparison. He knows what he's paying right now, ordering 327. Should he move from 327 to something larger, which means he's going to hold more inventory, but save on the total cost? So this is the question, and that's what we are following in our analysis. This will give you an idea how such an analysis is summarized. Okay, so between 1 and 2.99, the unit cost is $10. $10, my order is EOQ. My EOQ is 327. Do you see that I didn't continue this here? Now here's why. You are the buyer. You see that your optimal EOQ that minimizes your cost when you pay $10 a unit is 327. Would you go to the seller and tell him, okay, I'm going to order from you 327 for a unit cost of 10? I don't think so. Because if you want to order 327, the seller is willing to give you a discounted price. You see, 327 is falling in this range. So for the buyer to insist on this order, he is not operating optimally. He can do better. So when the order size, EOQ, is falling above the range that qualifies you for a certain unit cost, just decide to neglect this order size. It will never lead to a minimum cost. Listen, if you order 327, right, and this is the total cost that I didn't calculate for this policy using $10, well, just plug in $9.75 in the same policy and you pay less. So it cannot be optimal. Therefore, when 327 is above the 299, just stop and don't continue the analysis. Move to the next range. Here is the next range. We calculated it and we saw that the EOQ is 331. Well, that's for $975 a unit. And indeed, it's falling in the range here that qualifies you for the payment of $975. So this is a legitimate value to look at. Therefore, you can calculate total cost and make a comparison of this with no changes, just as is, to the other total costs that we are going to experience. Okay. Now comes the third one. The third one is calling for an EOQ of 336. This is if you pay $9.50 a unit. So you go to the seller and say, that's what I want to order. And he's telling you, no. If you want to pay $9.50, you have to start with an order of 600. So you, the buyer, might think there is a potential here for saving because I'm paying less per unit. What do? You modify your order size. Instead of 336, you move up to 600. 600 being as close as possible to 336. you see that here I wrote 331 under modified because the original EOQ did not have to be modified. So I placed 331 here. At the end of the day, these are the unit costs, not the unit cost, the order size that we are going to use to calculate total costs. So the question is why to move from 336 to 600 and not to 610, for example. I'll have a word about it in a second. Then you go to the next level. 337 is optimal for this unit cost, only that the seller is forcing you to increase the order to at least 1,000. And same here. So although 3 needed the modification of the EOQ upward. Now, why is it that you move from 336 to 600? I'm showing to you here. It's a last minute addition here that I did, I think, yesterday. And so I did not place it on a different slide, so I am apologizing. It's too stuffy here. Anyway, what do we see here? I'm starting at the level of 300 because I'm demonstrating what happens for this discount level. For this discount level of 975, this curve is the total cost. It's the regular EOQ total cost function. And it started 300 here. So this line is bold because the total cost exists on the range between 300 and 599. It is dotted line here because it does not exist beyond 599. So I just drew it here as if this is a hypothetical function. Not going to use it anyway. The next one is for a discount of 950. This is the second curve here. It's coming below the first one. So the first part of it is dotted. You see this one up to 599 because this function indeed starts at 600 from here to 999, from 600 up to 999, say. The function is moving up here. And that's the key thing. So what you see here, you see a first function go all the way to 599, then dropping, and start moving up from 600, but it's a different function. That's the total cost function that includes all the discounts in it. So we were here at 331 under 975. That's what we wanted to order, and we could, because we are in the correct qualifying interval. Then we wanted to use the second function. You cannot use 336 because this function doesn't even exist here. So we move from 331, it starts from 331 up to, or from 336 up to 600. Why not more? Because the total cost function here is increasing. So I take the lowest, and the lowest occurs at 600. So therefore you increase it from 336 to 600. And that's the modification that you see in this table. This is true for any other modification. These are the quantities that you have to use now to calculate total cost. So the second step was modify the Q. And incidentally, I added here, look in this graph, it just happened so that the minimum total cost is here for range number 2, it's level number 1, but the total cost here comes lower because of the discounted price. Is it always so? No. Sometimes this one comes higher than this one. But in this case, it came up lower. So in an order of 331 to an order of 600, 600 yields a better result. Now let's go to the calculations. Demonstration of calculating all those costs that lead to the total cost. I don't continue this one for the reason I told you before. For sure, this total cost is not going to be the best. Now, I go to the second one. Calculate the annual ordering cost as CO times D divided by Q. Which Q is this? 331. Remember, 331 is the EOQ of this range. I didn't have to modify it. I put it under modified because that's where the quantities appear in the table, but I didn't have to modify the EOQ. Then you go to the holding cost. So you have the CH. Okay, so it's 0.14 times 975. 975 is the unit cost, times the Q divided by 2. And give you the holding cost. Notice that the ordering cost and the holding cost are the same. This is no surprise. I mentioned it once to you. In the EOQ model, if you order the EOQ order size, the ordering cost is equal to the holding cost. So if you have to do it by hand, once you calculated one of them, copy it here, it will be the same always. Then you do the purchasing cost. So you take the unit cost here and multiply by D, and you get this. Then you add all of them, and you get the total cost. Okay. Now I go to the next. The next discount level is the one in which you have 50 cents discount. We know that the optimal order here for the EOQ per se is 336. We also know we needed to modify to 600. So therefore our Q is 600. The ordering cost then is CO times D divided the modified Q, 124. Holding cost. Now you take 0.14 times the new unit cost. So you see it's not the same like here. Times the Q, the new Q, divided by 2, and you get 390. Notice that these two now are not equal to one another. The reason is that 600 is not the EOQ under the price of 950. But I'm forced to use it because of the seller's schedule. And the holding cost is larger than the ordering cost, just as a comment. It's because you order more than the EOQ itself. So you have to hold more inventory and you pay more on holding costs, less on ordering cost. The purchasing cost is the new unit cost times the demand. You add them and you get 59,803. This is how you complete the next two levels of discount. And what you do now, you monitor your total costs. And you select the one that came up the lowest and obviously is the last one. So this solves the quantity discount model. It tells you that the optimal order is 5,000 units per order. It tells you that you will be paying 59,324. If you want to know how much you are paying, you have to calculate the total cost here, which I didn't do, and take the difference. But coming the template, it does calculate it, and you can easily tell. What is required from you is in a test. I guess you will be wondering. Normally, I'm asking you to show that you know how to calculate this total cost. The template doesn't show it to you. It just gives you the value. but it doesn't go into the details. So I want you to know how to do it for each range. And I am asking you to, I specify one single range and say, demonstrate that you know how. So sometimes you have a table with 6, 7 levels of discounts. I will never ask you to do all the 6. 1. And this takes exactly a minute. So when I told you before that you cannot forget about the EOQ, this is why. You will have to apply your knowledge of the EOQ model in order to do that. Okay. Another comment that I have about this huge quantity. This buyer used to order 327 units per order. So his maximum inventory at the beginning of the cycle was 327 units. Okay. Now, what if he has only room for 4,000 units? He cannot stock 5,000 units. Then he cannot order an order of 5,000 because there is no room for him. You know, this is a situation that might happen. The seller is very happy with this analysis because the buyer, if the buyer could, he will increase the order from 327 to 5,000. That's excellent for the seller. The only problem is the seller failed in the intelligence that he is applying before coming up with the chart. He didn't know that the buyer will not buy 5,000. So what should the buyer do now? Well, one option is to go to the next best. The next best here is 59388. Order 1,000 units instead of 5,000. Because that's the best that you can do if you can stock items after the 5,000. So that's one option. Another option might be a little bit more creative. What if the buyer decides to order 5,000 units? He's paying $9 a unit. Only that the moment he gets the order, he ships 1,000 units to charity. He now holds only 4,000. He has this warehouse for that. He paid for 1,000 units that he is not using, but he might get some tax deduction at the end of the year because of the donation. Yeah, well, never mind that. Then he has now to order as if the order size is 4,000. He's ordering 5,000, but he's using only 4,000 per cycle. So we have to recalculate his order. Unit cost is $9. Initial inventory is 4,000. And that's how he's calculating his EOQ policy, total cost. And then plug it in as one of the options here and see which one of them come with the minimum cost. Maybe it will be lower than this cost because he's taking advantage of $1 per unit discount. So it's possible that this will be the best policy. What I'm trying to tell you here that this is a school solution here, but the real world is full with other challenges, and you have to be very creative when you work. And this is the discounting all unit discount model. And the only thing I want you to know, okay, at the end here, I included some definition in words. What are the steps that you have just seen as an example? You may want to look at it. It's not adding more information, it's just putting it in words. And what I want you to see yet still is the template. There is a template called all units discounts. Do not look at the incremental discount. There is a template for that also. And when I say there is, I mean in the inventory template that appear on the website. So what do you enter in this template? You enter the demand here. You enter the unit cost without any discount, original unit cost. You pay, and then the EOQ information, H, this is CH, calculated by the template. Here is the ordering cost per order. And this is a problem that had a lead time that I enter here and safety stock. If there isn't, then you leave it blank. But now comes the discounting information. So the number one here is the default. The breakpoint for level 0 is 1. It will appear here in the template by default. And you have to enter the cost 10 if the template does not enter it by default. Copy it from here. Once these two are in, the quantity EOQ will be calculated. And then the modified Q will be calculated and the total cost. Notice that this is exactly the range I told you to skip if you do it by hand, but the template is doing it anyway. It doesn't take any time for that. So it just copied the 327 into the modified because this is how the total cost is calculated, and that's the total cost. Okay. Then you enter the first breakpoint. So in the chart, it was between 1 and 299. 300 is the breakpoint. 975, you enter these two, you'll get the results. The modified remains the same like the EOQ. Why? Because the EOQ is falling between 300 and 599. Now comes the next one. You enter the 600. 950. So EOQ is given to you here, but the modified becomes 600. For 600, here's the total cost. That's it. And that's how the template works. You don't have to work hard. It tells you here what is the optimal order and how much you pay total for that. That's what the template does. Okay. So this is the quantity discount model. And what I'll do now, I'll stop sharing just to see if you have any question. Let's see if there is any question. Nice. So if not, then I'll share again. Now I'm looking at the production. Okay. So this is an extension of the EOQ model again. The unit cost now is not quantity dependent, it's just in the EOQ. But the story here is, let me give you the equivalent of the EOQ model for the production lot size model. Suppose a buyer is buying huge order. The supplier cannot ship all the order in one shipment. He needs to ship it to you in daily, little by little. So it takes a week, say, to receive all the order. Now you cannot draw the right angle triangle that represents the inventory, because the inventory is not increasing in one vertical line. This is exactly what happens in the production lot size model. You have a manufacturer. he is self-producing in his own production system, takes the units, put it on shelf, have a store, and sell. He is distributing also. Once he does that, he is having now an inventory problem that he needs to solve to minimize his own costs. So the inventory he's building depends on what is the lot size that he's producing. So instead of ordering items, you self-produce them. Not all the production lot is received in one instance. And the reason is that usually production lines have their own speed. It's not infinitely fast. So it takes time to produce an order. It's called the production run. The production run takes time. So the inventory is not increasing with all the order in one instance. This creates a change in the geometry of the system. And now you have to adjust your total cost calculations. So this is exactly the analysis that we are going to follow now. You see those triangles that you see here are typical to a production lot size model inventory profile. The only thing I can tell you now is that all the production lots in different cycles are equal to one another because all the other assumptions of the EOQ model are true here. All the costs are not changing over time. The demand is a constant over time. And also the horizon is very long and shortage is not allowed. Everything that you have seen before is true here. The only thing is that the order is not received in one batch. And I don't call it order, it's a production lot, is not received in one batch. So how can we explain this behavior? Well, look at the difference between an EOQ model in which inventory increased vertically from this level of 0 to the maximum level, to this when there is a production and inventory increases gradually. But when you say inventory increases, we have to be careful. We have to see exactly how did we get this line. So here's a little explanation for that. Here is the machines, the production line work, and inventory increases at a rate of P. P for production. P is the production rate, which means the number of units that this production line can produce in a year if it's working nonstop. And at the end, the production lot size is Q. You can see it here. That's how many units are produced. It takes time. This is the production time. However, the moment you start the production and delivered items to your store, you can start selling. So demand is kicking in. It's kicking in, and therefore the inventory will not reach the level of Q at the time when you finish your production. This is how much you sold during the time that you were producing. And therefore the inventory is moving up at a rate that is P minus D, D being the demand rate, how many units you can sell per year. So the rate of increase of the inventory is P minus D, and you see it here. That's how the inventory is increasing. This inventory is not. You never have this inventory of Q units. This is the maximum inventory that you have. At this point, the production is finished. So what you are left with is the demand only. And the demand now behaves like an EOQ, is reducing the inventory along a straight line because it's constant. And that's what explains the triangle that represents the profile of the inventory over time. At this point here, new production is starting and a new triangle that looks exactly like this is starting. So this is what is typical to the production lot size model. The maximum inventory here is not Q. Q was here. But because the demand here was consuming some of the inventory, the demand is now Q times 1 minus D over P. D is the demand as P is the production rate. In this model, the D must be strictly less than P. The demand rate is smaller than the production rate. Of course, machines work faster than the demand created by the market. In 99% of the cases, when you have a coronavirus and the factories cannot produce enough inhalators, then you have some problem because demand is in a peak. But we are not talking about that. We are talking regular situation that is balanced. And so the demand is larger than, is smaller than the production rate. And therefore D divided by P is a fraction. And 1 minus D over P is also a fraction. It's less than 1. So Q times it is less than Q. Q was here, and the maximum inventory is here. I can also show why is it 1 minus D over P, but never mind the math. Okay, so what we need to do now is to look at the total cost. The total cost function is similar to the one that you have seen for the EOQ model with only a few slight changes. CO used to be the ordering cost per order. There are no orders here. There are production lots. So CO now is the setup cost, not ordering cost. Each time a production starts, you have to prepare the production line. This might take time, it might be expensive, but it does not matter at all how many units you're going to produce. CO remains the same. You have to prepare the line. You have to clean machines, you have to recalibrate machines, you have to bring raw material, you have to change the crew. Preparations takes time. So if they take time, it costs money. So CO will be the setup cost per setup. P, as I said, is the annual production rate. It will be part of the model now. And everything else that you have seen in the EOQ will be there too. Okay, here is the total cost function. So the total cost is a function of Q. Q here is not order size, is the production lot size. This is the holding cost per year. I'll have a word about it in a second. This is the ordering cost per year, and this is exactly the same as in the EOQ. The only difference, this is now a setup cost per setup. This one is not a purchasing cost. This is the production cost. C will be the unit production cost. So now the holding cost. Holding cost is calculated as CH times the average inventory. Average inventory is all this term that you see here. Well, for the EOQ, it was Q over 2 only. But for the production, you have to adjust it by 1 minus D over P. Why? Why is it so? So the average inventory I showed you before is Q times 1 minus D divided by P. That's the average inventory at this point. So not the average, the maximum, I'm sorry, the maximum inventory is Q times 1 minus D divided by P. So the average inventory is here. So it's the maximum inventory divided by 2. So take a look. Here is the average inventory. CH is multiplied by the average inventory to get the annual holding cost, just as it's done in the EOQ model. And this is the difference. So once you solve this equation by minimizing it to find the optimal Q, you get Q star. Q star represents the optimal production lot size. And it's very similar to the EOQ model. You have a square root, 2D times CO divided by CH. That's your EOQ, but you have to adjust it by 1 minus D over P. Again, I could show it to you. Why is it so if I had the time? Never mind. I don't want to. It's a little bit of math, but not more. Okay. What else we want to know here? Some interesting times here, and it is the cycle time is the time between 2 consecutive production points. So Q divided by D, exactly as it done in the EOQ model. Okay. And then comes T1. This one you did not have in the EOQ model. What is it? You have the time from this point all the way to this point here. This is when the production line was busy producing the item. So you calculate it as Q divided by P, and here's why. You see the example? Let's say the production rate is 8,000. 1,000 means that in 1 year, the production produces 1,000 units. Let's say that I decide to produce only 100 units now. How long will it take me? It will take me 1/10 of 1 year, 100 divided by 1,000. So Q divided by P gives you T1 in years. Now, if you want to make it in months, then multiply by 12. But that's the answer for T1. T2 is the time when the line or production line is not producing the item. So it's the cycle time minus T1. See, cycle time minus Q over P. In here, I show it as Q times 1 over D minus 1 over P. So I took the Q outside the parentheses and multiplied by 1 over D minus 1 over P. Okay. These are the interesting times here, and now let's see a little example. I'm telling you, this is an example that I've taken from the text. I don't know if Farah is sitting here, but I did not decide the name. We have a girl called Farah Al-Farah, and so I was hesitant about including it. But this is the text example. And this is a manufacturer that produces some lipstick. Okay. The information is that the factory is open 7 days a week, 24 hours a day, and the production is 1,000 tubes per hour. These two together gives you the annual production rate P. We do it. Now there is some setup time that is 30 minutes. You know, it's very short. Doesn't take much to prepare a production line to produce lipstick in this example. So because of that, I don't even include it in the solution, but I want you to know sometimes production times are long. You cannot ignore them, because when the line is being prepared, the line is not producing. So the time it can produce out of a cycle becomes shorter. Right now, we calculate the cycle time as Q divided by D. But if there is some time within a cycle when the line is not producing, this calculation is incorrect. We don't have this problem in here because I just ignore the 30 minutes. How do you handle it when you have longer cycle time? I'll leave to someone else to tell you. It will not be part of our discussion. Now, the setup cost is $150. Each time you spend the 30 minutes, it costs you $150. This is not something to ignore. The demand in dozens is 980 per week. So now we can calculate the annual demand. And the unit production is 50 cents, and your annual holding rate is 40%. So it's 0.4. Now, in order to solve the problem, we have to know the annual demand. So take a look. 980 dozens, it's per week, multiplied by 12 because we have dozens, divided by 7 days a week, times 365 days a year, give you the annual demand. And CH is just H times C, and ordering cost, setup cost is 150. Now come the production. So you have 1,000 units, and that's per hour, times 24 hours a day, times 365 days. So this gives you the production rate. Notice that this value is very small compared to this value. Under the current policy, the company, and if you read the problem, that's what they say, is ordering 84, is producing each time 84,000 tubes. And the company wants to know if it's even close to the optimal and how much money they can save. And in addition, I just add some more values here. The cycle time, Q divided by D, it's 0.137 years. It's about 15 days, 50 if you multiply by 365. The production time is Q divided by P, which is 0.0096, about 3.5 days if you multiply by 365. And now I entered something, I don't think it appears in the book, but it's an interesting observation. What percentage of the time the machine, I call it machine, it's a production line, is busy producing the lipstick? Well, in one cycle, the percent is T1 divided by T times 100 in one cycle, and it becomes 7%. But each cycle is identical to the other. So in each cycle, the machine is producing only 7% of the time. So in the whole year, the machine is busy only 7% of the time. It's idle 93% of the time. Well, this is a very poor manufacturing design. You do understand that. A production line is expensive endeavor. You invest in the machines. A lot of money might be invested there. You don't want the production line to not work. You want it to work non-stop. And this one means that this lipstick occupies the production line only 70% of the time, and at the rest of the time, if there is nothing else happening, the line is idle, doing nothing, waiting for the next production run. Well, normally it's not happening this way. Normally you have several items, all produced on the same line. So the utilization of the line around the clock is much larger than this. But now you understand why the setup time is important, because if you schedule more than one item on the same line, then these other items can be produced on that line when it's not producing the first item. But then it has to move from one item to the other. So that each time it moves, there is a setup time and another setup cost. And this is the real production control problem that goes in the real world. Sequencing of items on a production line is a very important issue and not always hard to solve for companies. That's because moving from part A to part B requires, say, a day to set up. But moving from part B to part A requires, say, 2 days. And so how do you sequence it to minimize the setup time is an issue that has effect on costs. But this is just a comment on the side that I'm giving you to get some understanding. We are having 7%, and this is it. I just want you to pay attention to the real world. The time that the machine is not producing the item and is probably idle per cycle, this is one cycle, is about 46.5 days. And this is what I wanted to know about this production lot size. The last thing is the total variable cost. I put the total variable cost for no special reason. If I add here the production cost, it will be the total cost. And then as a matter of comparison, I put here the optimal order. I found it from the optimal production lot size formula. So 2 times D times CO divided by CH, 1 minus D divided by P. And you get 31,500, say, 31,499. This is much smaller than 84,000, but this is optimal. And the total variable cost is 5,850 compared to 8,000 something. So there is saving of about $3,000 by just moving to the optimal policy. Okay. The last thing I want to show to you is the template here. So you have the demand that you enter, you have the unit cost, you have the H, then the template will calculate CH. You put CO and you put the P, don't forget the P. This will give you all the results here of the optimal solution. And just one comment here, you can also enter the current policy, the 84,000, and it will give you all the information here, including total cost. Total variable cost doesn't matter. And then you can see how much money is saved, see? So this is what I want you to see in these 2 inventory models, okay? And let me ask, is there any question before I leave the sharing? No. And let's see if there is question to figure out if adequate shelf, do we use maximum inventory or average inventory? Do you hold the average or hold the maximum? That's my answer. I think it's clear. You have to have enough inventory for the average inventory. This is my answer. Okay, Duran, Mr. Duran. And from Hector. Oh, you say it's 2:18. Yeah, I scheduled an hour and 30 minutes, but I'm done. If you are in a hurry, you can leave. Okay. So I'm done for today, and I'm waiting for your assignment. I think this will help in the assignment, of course. It should not take you long. I have to say, do some for yourself, some calculation on the side, and just enter the letter. Whenever I'm asked, show your work, and we'll continue from here. So the model that we are going to do on Thursday is an EOQ-based model, don't get me wrong, but the demand is going to be a new creature. Now it will not be constant. It will be uncertain. This means that some probabilistic approach will be needed, and that's what we are going to do on Thursday. Okay? Then we'll start something new. Okay, everyone, thank you for being here. And if you want to make any comment about today's, and if it was clear enough and you can now study on your own, tell me that right now before you leave. Yes, no, yes, no, yes, no. Okay, okay, okay. I hope it was helpful, and we'll meet again on Thursday. You can come tomorrow, it will be the same, but Thursday for you. Okay. The reason, by the way, I scheduled the assignment for Friday is because I wanted to make sure that I'm covering the two models, and I didn't know ahead of time that I'll have time for the two models. That's why I made it Friday. But I see that I finished everything. You're on your way. So can I say bye-bye right now? Okay, bye-bye, everyone.
Have a good day, Professor. Just a quick question. Do you have office hours?
Well, I don't know how we can do office hours. You want office hour before what?
Before the quiz or before the exam?
Yeah, of course I can do it. It will be between 9 and 10, maybe once a week, maybe on Tuesday. I don't know how useful it is, because, you know, if it is useful, I'll do it. It's not this. I don't know how, because I have to talk one student and there will be 10 others sitting and listening. I can do it. Really, I don't mind. I don't mind. So I'll schedule it. Let me see exactly when. Next week, okay?
Sure. Thank you so much.
The quiz is coming up on the 21st. What, on the 20 or 21st, the quiz.
Okay, we'll write it down.
If you have the syllabus, you'll see.
Yeah.
21st. So let's do it a few days beforehand. Now, if anybody wants another office hour and an email to me with an answer from me is not enough, just ask. I'll find time for that. Okay? Okay, so I hope you have enough support for what you need to do. You know, it's a different mode of learning. What can I do? It's what we have. Do the best you can, guys. I do the best I can. Do the best you can. Okay?
Thank you.
Bye-bye.